So it's not a high-level talk. It's more a technical talk about the internal of Python. And my hope is that after this talk, you will be able to understand why in some case NumPy is slow and why in some case NumPy is fast, why Python has this hybrid mode. It just gives you a few keys to understand that. And my name is Serge, by the way. OK, so whenever you see Python code, it's Python 3, obviously. And whenever I speak about Python or the Python interpreter, it's the CPython implementation. OK, some things I will tell you are valid for other interpreter of Python, like Gpython or PyPy, but some of them are not. So this is the assumptions. So one should not forget that Python is a glue language. It's now used as a general purpose language, but that's not where it comes from. Okay? So many of the issues you may have with the Python language are directly linked to that. It's not meant to be used to do number crunching. That's not its goal. It's meant to write wrappers around C libraries. If to gather this list, I just find all the shared libraries in my Python install directory. So all this library contains some shared library inside. So that's Python code, but inside it's running native codes. And many modules in the Python interpreter are indeed native modules. So there is not a single line of Python inside. So from the beginning, it's C code wrapped with fancy stuff and bells. But remember, there is always two words. There is a native word and the interpreted word. And at the core, there is this PyObject. A PyObject is just a piece of data managed by the interpreter that encapsulates whatever you want. So when you manipulate a string, an int, a list, any object in Python is a PyObject internally. It's just a pointer to some memory, which itself contains pointers to other places in memory. So you've got a PyType, you've got the reference counting, and you get, in the end, the actually wrapped object. So we call that a wrapped or a boxed value, because the value is inside the box, and this box makes it easier for the interpreter to do stuff, but there is a price. And once you realize that everything is boxed in Python, then a list, which is used as std vector in C++, it has none of the good property std vector has, because it's just a pointer to some memory area that contains itself pointer to other memory places. So it's nice because you can write objects with different types inside a sequence, because it doesn't matter. It's all the single same type from the interpreter point of view, at least at that level. But there are consequences, so good consequences. It's a good design choice if you want to quickly write an interpreter, because everything is done at runtime. You don't you don't impose memory management to the user. Everything is checked when used. But there's also great costs. First, you keep every time you need to access the actual value, even for an int, you need to look inside the box. That's called unboxing. So the interpreter does that for you, but it means an extra indirection, which in terms of memory locality is not good. In terms of efficiency, it's not that good either. It means more memory usage, because each time you use an int, you need to create this small box with all the type information or type references. And this costs extra memory. So the memory consumption is going to get higher than native equivalent. And it also means memory fragmentation. Even if you can customize the memory allocator used by the Python interpreter, basically, each time you create an object, you have at least one malloc running, or one memory allocation running. And so instead of having everything in the same place, which is good for cache and so on, your objects are just living somewhere in memory, and you don't have any control on that. Which doesn't matter, because remember, it's just for wrapping libraries. So you should not care about performance. But then you begin to use Python for other tasks, like number crunching, numerical operations. And so you keep on crossing the frontier. This frontier is very important to understand how Python works. There is the interpreted word and the native word. And whenever you do something at the interpreter level, there is actually a boundary crossing to go into native code, doing some stuff, and then go back to the interpreter. When you type 1 plus 2, there is some lookup and so on, but basically, you're looking into a Py object and dereferencing stuff in the native word, and then building a new Python object and returning it to the interpreter. Whenever you do that, you're paying a cost. And if you want to automate the writing of native code, that is, you have your C library and you want to call it from Python, then you need to manually create this Py object because you have your real values and you want to box them, to wrap them. And doing that manually is tedious because you need a lot of glue code. It's costly in terms of efficiency because of the unboxing operation that costs, or that may cost a lot. And you need to be careful or to understand the underlying model. So let's move on. The tedious part is actually not the most difficult one because there is a lot of alternatives to automatically box and unbox objects in Python. So you've got in the standard library the ctypes module, package, which make it possible to explicitly state you need to box this value as this type or to unbox this value as this type. So you're doing it at the Python level, but it's explicit. You can write your C code calling the Python C API to manually create the objects. And I have a few examples of these two situations later on. You can use an automated way to do the wrapping and unwrapping. So that could be CFFI, Dragon FFI. Surprisingly, Cython is also used a lot just to generate the wrapper, even if it's not its primary goal. It achieves this goal very efficiently. C++ developer or C developers that are not afraid of C++ can use PyBind 11 to have a C++-like interface to build to do the boxing. And if you want to target multiple language, you can still use Swig, but it's so previous century. So, okay, you can automate that part, but then you need to understand what you do. So those are two pieces of code. The first one is Python, and the second one is C. It looks the same. I have my object, L, and then I'm getting an item inside, the first one, and then I'm unboxing it as a C value, a long, and then I'm updating the value. But it's different because the Python code updates the value inside the list, while in the C code, we update the unboxed value, which is a copy of the value that was inside the Py object. And so we should update the value inside the object, crossing the frontier twice, while it looks the same. But it's different because we are at interpreter level in the Python code, and we are in both interpreter mode and native mode because we have Python code and native code mixed. So whenever someone speaks about the GIL, say, oh, there's a GIL, so a lot of bad stuff. It's just because many operation on the Py object needs a lock. Okay, so this is not locked. Well, this is not locked, and this is not locked, actually. Oh, get item implies a lock because I'm creating a new, I'm updating the reference count for the item inside the list. And so there is a small lock taken and released inside that. So the lock is just whenever you perform some operation on the Py object, you need to be sure you're the only one that increments the reference counter when you do it. Then you want to decrease the cost of boxing and unboxing values. And basically, it's not possible. right? It's the price to pay. Whenever you want to access the value inside the Pi object, there is a cost implied, and you can't go around that. Well, actually, there are workarounds, but they imply trade-offs. So the first thing is, if you know for sure your object is going to be of a given type, then maybe you don't need to check its type, and you just unbox it and say, this is a long. And if it happens to be a string, then you will cast some random value as long, and you just get crap. But then you're faster. Okay, so if there is a contract between your user and you that this is going to be of this given type, then you can just skip some checking. Obviously, you don't want to do that on a regular basis, but at least you know that you're paying this price. Then you can stay in mixed mode. Mixed mode is you have native code and calls to the Python C API mixed into the same function. And that's OK. If your number crunching part is only for part of the code, then don't unbox the other one, because you can just do the regular Python C API calls and unbox only when it's needed. So that's typically what happens when you use Cython. When you use Cython, you have this colored output in HTML where you see part of the code is in Python mode and part of the code is in native mode. And you don't care if you only optimize the loops, then the other parts don't need to be unboxed. Okay? So running in mixed mode is a good way to avoid some costs. Then you may also think about your API. And that's mostly the most important part of my talk. If you have a fine-grained interface, whenever you do a small stuff, you export it as a function, you imply a lot of border crossing. And so if you were born in more than 20 years ago, you remember before Europe, whenever you cross the boundary, you spend time. Okay? While on my last holidays, I went to Italy, and crossing borders was costless. But it's not the case in Python. Python is not like Europe. Whenever you cross a boundary, you need to pay. And so if you export each small function in your library and do a lot of back and forth travel, then you're going to pay. And wait, there is one library that you all know that does that a lot. It's NumPy. Whenever you call a NumPy function, a NumPy whatever, indexing an array, broadcasting, you're crossing borders. So now you understand why a for loop is not good, because you're going to do the for loop at Python level, and each time you index, you've got this back and forth travel, and you're paying for that. And you don't want to, because you're just adding two integers. That's why ufunc are good, because you only go once in the native world, do your stuff, and then get the object back. But that's not enough, because when you do A plus B times C, there are two travels, one for A plus B, and one for the result times C. Or no, that's one for B times C, and then for the plus. And so it prevents optimization across the code. You can't say that's an FMA, fuse, multiply, add, because you have a boundary, right? That's why calling matrix multiply is even faster. So the higher your API, the easier it is to optimize it at the native level. The other way of not costing less is start unboxed. When you create a list, the list is created in Python. And then you may want to use it in the native world, and then you need to decapsulate everything. But you could also say, my object is created and should live mostly in the native world. And sometimes it will appear in the Python world. And that's what NumPy does. NumPy creates one single bunch of data in the native world. If you want to access it in the Python world, then it's costly. But if you do most of your computation in the native world, then it's not as costly as it is. That's why converting a Python list is in big O of n, because you need to decapsulate each element in your list. While for a NumPy array, as you're only passing a pointer back and forth, it's in big O of 1. So it depends on your usage. So why are managed fine-grained operation on NumPy array costly? It's because just like it's costly to cross the frontier from Python to native code for lists, it is costly to do it the other way for NumPy. It's just that lists are meant to be used in the Python world, in the interpreted world, and NumPy array are meant to be used in the native world. You can also just don't expose your object at the Python level. There is one thing that is normally only available in the C API. It's called PyCapsule. So you can create that with PyCapsule new. And it just says, OK, this is a row pointer to anything in memory. You can pass that to the interpreted word. It will just copy the pointer. But you can't do anything with it in the interpreter. The only thing you can do is pass it back to the native word, which knows how to decapsulate and interpret this void star pointer. So this is a small illustration of going back and forth from Python. So I'm using C-types here. C-types give you an access to the Python C API through Python API. And then I'm accessing PyCapsule new. So I've got which is a function. But it's untyped. It's just a row pointer. I'm using the C-types API for the type, which means that I know how to perform the unboxing because I know the types. So that's res type and arc types. Then I'm loading a native library. I'm extracting a function pointer, which is cubic root, which does not exist in NumPy, so I can use that more efficiently if I want. And then so this is just a row C pointer, and I'm putting this pointer into a capsule, which means that now I can pass this to the native word and just have a look inside the capsule, get the row pointer, and use it from C. Okay? So I have a pointer that comes from a shared library, so from C. It's back into the interpreter thanks to C-types. And then I'm going back to the native word using capsule. So you can go back and forth between the two words. It's just a matter of using the right tools. So now, just to make sure you understood this whole crossing frontier stuff, I've made a few examples. Those are Python code plus Python annotations that basically describe the type. And Python is capable of compiling this Python code into pure native code. And the only border crossing that happens is at the frontier. That is for the arguments and for the return type. So how many times, if I call quiz 0, do I cross the frontier? Two times. One for the argument and one for the return. And inside, everything is done in the native word. No extra cost. So this is an ND array of one dimension. Same code. How many unboxing happens? Oh, N is obj. That's a typo. Thank you for pointing out. So I still have one border crossing for the argument and one for the return value. Okay? But as it's an ND array, the border crossing is just copying a pointer plus a few shape stuff. But basically, it's in big O of 1. So it's not costly. While if I do that, how many conversion do I have? A lower bound. So the lower bound is 2, because I'm at least getting a list and returning something. But actually, it depends on the number of elements in the list. If I have n elements in the list, then I will need to convert the actual list and then the n elements, which are integers. And the other way around, so Python is going to create a list because it can't create, because it's a list comprehension. So I will create a list and then fill each element. And so that's very costly. Okay, crossing borders in that situation is very costly. Is there an issue with that code? So I'm just popping an element. So let's assume that there is one element, but otherwise exception throwing is supported. But OK, I'm still returning something. I'm returning node. So I'm not creating a value in that case. I'm just incrementing a reference counter. I'm doing a lot of unboxing because I need to create a native set out of the Python set. But more than that, I'm updating a copy. Because I've made a copy, a native copy of my set. I'm updating the copy and just returning. Because that's a semantic change compared to the original Python code. Because the Python object will not be updated because I'm working on the native copy. What I should do, and Python does not doesn't do that, is copy back any change from the native word back to the Python object. But that would be very costly, so we don't do that, and we just document the behavior. That's almost the same example. I'm updating an object. But this object is no longer a set. It's an ND array. In that case, so I still have one reference counting increment because I'm returning node implicitly. I have one conversion of a pointer. But as I'm only updating the value pointed, one of the value pointed by this ND array, and the original word for ND array is native, then the update will be seen at call site. Because both views, the native view and the interpreted view, are looking at the same memory pointer, right? This one is slightly more complicated. The first argument is a function. But this function is actually a function passed through a capsule. Okay? So I have a native function that gets passed as first parameter of my function. I'm calling it on a native value because it has been converted. So there is still two conversions for the argument and one conversion for the return value. Unboxing the capsule is big O of 1. Unboxing an integer is big O of 1, 2. And then calling capsule on value, capsule is a function pointer to a native function. Value is also a native value because it has been unboxed. So there is no unboxing happening there. Correct? You can create capsule through Cython too. Okay, you can create capsule through any C code. And it's sometimes useful, for instance, for higher level functions in SciPy where you can provide your own function as a parameter of anything doing, I don't know, a convolution or whatever. So thanks to all this example, I hope you now understand why NumPy is sometimes slow and why it is most of the time fast and why it can be faster when the compiler optimizes it because it removes this border crossing. PyPy aims at being a JIT implementation of Python that supports all the API, which includes native modules. And so it's complex for them because they have their own version of what is interpreted. And so they need to manage the difference between their version of interpreted word and the one exposed as part of the standard API in the Python C API. And so there is no doubt it's difficult. OK, now you understand why Cython does what it does. It just removes some border crossing, but not all of them, and you can choose explicitly. And if you don't understand any of these points, well, you still have time for questions. So just ask why, and then this sentence, and I could explain again.